The universe is not empty between galaxies. It is threaded with something invisible. Across the voids separating galaxy clusters, stretching across millions of light years, exists a magnetic field so weak that no instrument on Earth could measure it directly. Its strength is roughly 10 to the power of -15 Gauss in the deepest voids. That is 1/400,000th the strength of Earth's magnetic field at the surface. A compass needle held in that field would feel nothing for billions of years of exposure. Yet the field is real. It fills the universe, and nobody knows where it came from. That single fact has occupied cosmologists for over 2 decades of serious investigation. Every known source of cosmic magnetism creates fields near the structures producing them. Stars, supernovae, galaxies, and quasar jets generate local fields, not cosmos-spanning ones. The voids between galaxy filaments are the emptiest regions in the observable universe. No stars burn there. No galaxies anchor the space. No black holes spin and radiate energy. Every standard cosmological prediction says those voids should contain essentially no field. What the Fermi Gamma-ray Space Telescope revealed over years of observation says otherwise. Before Fermi, the standard picture of the cosmic web had one persistent assumption in it. The web consists of dense filaments of galaxies and vast empty voids between them. Filaments carry gas, dust, stars, and every magnetic field that stellar processes generate. Voids were the leftover space, the regions where matter never concentrated significantly. Cosmologists expected voids to be magnetically clean, pure vacuum on cosmological scales. That expectation turned out to be wrong in a way nobody had specifically anticipated. Fermi was launched by NASA on June 11, 2008, to survey the gamma-ray sky with new precision. Among its prime targets were blazars, active galactic nuclei whose jets point at Earth. A blazar produces gamma rays with energies reaching hundreds of billions of electron volts. Those photons travel across billions of light years before entering our solar system. Along the way, they interact with infrared and optical photons that fill intergalactic space. When a very high-energy gamma ray collides with a background photon, both particles annihilate. The products are an electron and a positron, created from pure energy in intergalactic space. That electron-positron pair immediately begins generating new radiation through scattering. Each scattering upscatters a microwave photon into a new gamma ray at somewhat lower energy. That secondary gamma ray travels outward and may produce another pair, repeating the cycle. The result should be a cascade, a spreading halo of secondary gamma radiation around blazars. Astronomers had calculated this cascade in careful detail for decades before Fermi launched. The prediction was unambiguous. Distant blazars should appear surrounded by faint secondary halos. When Fermi observed distant blazars with enough exposure to find those halos, they were absent. The secondary emission that physics predicted should exist simply was not present in the data. The absence was not immediately obvious. It required years of accumulated observing time. A faint halo around the bright source is a subtle signal requiring careful statistical treatment. Multiple groups analyzed the Fermi blazar data independently using different methods and samples. All arrived at the same conclusion. The predicted halos were missing from the observations. Neronov at Geneva and Vogt and Max Planck published their landmark analysis in Science in 2010. Their paper established the logical chain connecting absent halos to a present magnetic field. If a magnetic field exists between the blazar and Earth, it deflects the cascade electrons. Deflected electrons do not upscatter photons along the original line of sight toward Earth. Instead of a coherent halo near the blazar line of sight, the cascade radiation spreads wide. The secondary emission is diluted across a larger angle, falling below any detectable threshold. The missing halo is therefore direct evidence for the presence of the field that prevented it. To deflect electrons sufficiently, the field must reach at least 10 to the -15 Gauss. That lower bound is firm. A weaker field would leave halos visible to Fermi's detectors. Subsequent analyses by multiple teams confirmed the Neronov result using independent approaches. Each study used different blazar samples, different statistical methods, different energy ranges. Each arrived at a consistent answer. Halos were missing, and the intergalactic field was real. Tanmay Vachaspati at Arizona State University reviewed dozens of such studies through the 2000s and 10s. His assessments found the evidence robust against all proposed alternative explanations. By 2015, the intergalactic magnetic field was treated as an observational fact, not a hypothesis. The question had shifted from whether the field exists to where it could possibly have come from. To appreciate why the origin matters, consider what we know about magnetic field generation. On Earth, the magnetic field arises from convective motion of liquid iron in the outer core. Electrical currents flowing through that conducting fluid generate the planetary dynamo. Without the core's motion and conductivity, Earth's field would dissipate within millennia. Stars generate magnetic fields through analogous convection processes in conducting stellar plasma. Galaxies amplify weak seed fields through turbulent motions of ionized gas over billions of years. The turbulent galactic dynamo takes a small seed field and amplifies it by many orders of magnitude. Without any seed at all, the dynamo has nothing to work with and produces nothing from scratch. The intergalactic voids contain none of the structures needed for any of these mechanisms. No conducting fluid flows there, no turbulence stirs the space, no sources of energy drive it. A field in the voids cannot have been generated there by any mechanism cosmologists currently know. The field must have spread from elsewhere into the voids, or it must be primordial by origin. Primordial means present before galaxies formed, before any astrophysical source existed at all. The propagation hypothesis, that the field spread outward from galaxies, was investigated first. Galactic winds driven by supernovae and active nuclei can expel magnetized plasma outward. This process magnetizes regions immediately surrounding galaxies, the circumgalactic medium. The magnetized outflow extends perhaps a few megaparsecs beyond the galaxy in favorable cases. But voids span tens or hundreds of megaparsecs, far beyond the reach of any galactic outflow. Detailed simulations of field propagation from galactic sources consistently fail to fill voids. The field strength falls off too steeply with distance from any source within a galaxy. By the time the field reaches the center of a large cosmic void, it has become negligible. The observations show 10 to the power of minus 15 Gauss throughout the voids uniformly. A post-formation galactic field would show a steep gradient, high near galaxies, zero in voids. The observed field shows no such gradient. It fills voids as uniformly as it fills the filaments. Uniform void filling requires a source that predates the formation of all large-scale structure. The field must have been present before galaxies existed and before the cosmic web condensed. That constraint pushes the origin back to within the first few 100 million years at most. Further analysis of the field's spatial properties pushes the origin much further back still. When the universe expands, magnetic fields are diluted by the growing scale factor squared. A field present at any early epoch will be measurably weaker today by a calculable factor. Working backward from the measured void field today, we can calculate the required primordial seed. The required early field is physically plausible under several different early universe scenarios. The question has become not whether a primordial field is possible, but which process created it. Three main categories of hypothesis have dominated theoretical discussion since the early 1990s. The first category invokes inflation, the period of exponential expansion in the first second. During inflation, quantum fluctuations on subatomic scales were stretched to cosmological distances. The density fluctuations that became today's clusters originated as quantum noise during inflation. If electromagnetic fluctuations were similarly stretched, a cosmological seed field could result. The problem is that standard electromagnetism has a symmetry property called conformal invariance. Conformal invariance means the electromagnetic field decouples from expanding spacetime completely. A conformally invariant field dilutes as the universe expands, rather than being amplified by it. To produce a magnetic field from inflation, conformal invariance must somehow be broken first. This requires new physics beyond the standard model, additional fields, or new coupling mechanisms. Mechanisms proposed include coupling to a scalar field, curvature couplings, and varying constants. Each mechanism produces different predictions for the field strength and spatial structure. Some produce fields far too weak to explain the Fermi observations by many orders of magnitude. Others overproduce the field, creating tensions with well-established cosmological observations. Getting the amplitude right generally requires tuning parameters with no independent motivation. The inflation hypothesis has one powerful attraction. It naturally produces uniform void filling. A field stretched by inflation fills all of space identically, with no gradient near any structure. That uniformity matches the observations better than any astrophysical source hypothesis could. But the lack of a compelling realization that derives the correct field amplitude remains a problem. The second category invokes phase transitions in the universe's first fractions of a second. The early universe passed through several dramatic transitions as it cooled in its first second. The electroweak transition occurred at roughly 10 to the minus 12 seconds after the Big Bang. Before it, electromagnetic and weak forces were unified into a single electroweak interaction. As the universe cooled below the electroweak energy scale, the unified symmetry broke spontaneously. The electromagnetic and weak forces separated into their distinct identities at this exact moment. This symmetry breaking did not happen smoothly and uniformly throughout all of space at once. It proceeded through nucleation of bubbles, regions where the new broken symmetry phase appeared. Those bubbles expanded, collided, and merged, completing the transition across all of space. At the boundaries where bubbles collided, electrical currents flowed, and magnetic fields formed. The collision process was violent and turbulent, stirring the primordial plasma in complex patterns. Tina Kaniashvili at Carnegie Mellon University and collaborators have studied this extensively. Her group has published dozens of papers calculating the expected field from electroweak processes. The results show the electroweak transition can produce fields of the correct general magnitude. The generated fields were spread further by magnetohydrodynamic turbulence in the cooling plasma. That turbulence mixed and redistributed the field across larger scales as the universe expanded. The spatial correlation length of the result encodes information about the specific transition. The QCD phase transition offers another opportunity for field generation in the early universe. This transition occurred at roughly 10 to the power of minus 5 seconds after the Big Bang. Before it, the universe was filled with a plasma of free quarks and gluons at extreme density. As the temperature dropped below the QCD scale, quarks became confined inside protons and neutrons. This confinement transition produced turbulence and current generation throughout the plasma. The resulting magnetic field would have a different characteristic scale than the electroweak field. Both transitions may have contributed to the total primordial field in overlapping cumulative ways. Disentangling their relative contributions requires measuring the field's spatial power spectrum. A fourth possibility connects magnetogenesis to baryogenesis, another deep cosmological mystery. Baryogenesis is the process that created the universe's asymmetry between matter and antimatter. The standard model predicts equal amounts of matter and antimatter should emerge from the Big Bang. Yet the universe contains overwhelming matter and essentially no primordial antimatter anywhere. Some mechanism during the early universe created this asymmetry before annihilation was complete. That mechanism has never been identified with certainty, despite decades of theoretical work. Some scenarios of electroweak baryogenesis predict magnetic field generation as a direct byproduct. The same currents that created the matter asymmetry may have created magnetic field lines directly. If this connection holds, the same physics explaining matter domination also explains the field. The overlap between these two deep mysteries makes the combined scenario theoretically attractive. It also produces a distinctive observational prediction testable with future gamma-ray instruments. The prediction involves magnetic helicity, a measure of how field lines twist around each other. In a helical field, lines wrap around each other with a consistent handedness throughout all space. Right-handed and left-handed helicity correspond to field lines twisting in opposite directions. Net helicity in the intergalactic field would be a signature of parity violation at its creation. The electroweak interaction violates parity. It has a fundamental preference for one-handedness. If the intergalactic field was created during electroweak processes, it should carry net helicity. If it was created by a parity symmetric process, its helicity should average to 0 overall. Detecting helicity would directly implicate the electroweak era as the source of the field. Not detecting helicity would rule out certain mechanisms and strongly favor others instead. Levon Pogosian at Simon Fraser University has developed methods to search for this helicity signal. His approach uses polarization data from gamma-ray observations of blazars at multiple distances. A helical field breaks the symmetry between deflections in opposite senses across the sky. The resulting asymmetry in cascade patterns carries the helicity imprint across cosmic distances. Detecting this asymmetry requires many blazars, spanning a wide range of positions and distances. Future gamma-ray instruments with higher sensitivity would make the helicity search far easier. Measuring helicity is one of the highest priority goals in intergalactic magnetic field research. The Square Kilometer Array is the most ambitious radio instrument ever built for this investigation. SKA is being constructed across South Africa and Western Australia in 2 separate phases. Phase 1 involves hundreds of dishes in South Africa and thousands of dipole antennas in Australia. Phase 2 will add thousands more stations and dramatically increase the total collecting area. The combined instrument will dwarf every existing radio array by roughly an order of magnitude. Its primary method for probing the intergalactic magnetic field is Faraday rotation mapping. When polarized radio waves pass through a region with magnetic field and free electrons, the plane of polarization rotates by an amount proportional to the field strength along the path. By measuring rotation measures of millions of background radio sources distributed across the sky, SKA will build a 3-dimensional map of the magnetic field structure throughout the cosmic web. Current surveys measure rotation measures for thousands of sources across the whole sky. SKA will measure rotation measures for millions, roughly a 1,000-fold improvement overall. Where current surveys have hundreds of sources per square degree, SKA will have tens of thousands. That density improvement transforms Faraday rotation from statistical sampling into near tomography. With enough sources along each line of sight, the field can be mapped layer by layer through space. Filaments, voids, cluster outskirts, and transition regions between them can all be characterized. Detecting the field in the deepest voids requires specialized analysis beyond standard methods. Void regions have very few free electrons. The density is orders of magnitude below filaments. Low electron density means a low rotation measure, even if a Fermi implied field is present. Extracting the void signal requires stacking hundreds of sightlines through void regions together. Individual rotation measures from void lines of sight are dominated by noise and measurement error. Averaging over many sightlines suppresses noise while preserving the coherent void field signal. This statistical approach demands precisely the source density that SKA will provide. The Cherenkov telescope array provides a complementary approach entirely from the gamma-ray side. CTA is being built at 2 sites, La Palma in the Canary Islands and the Atacama Desert in Chile. Together, they cover gamma-ray energies from around 20 giga-electron-volts to 300 tera-electron-volts continuously. CTA's sensitivity exceeds any existing imaging Cherenkov telescope by roughly a factor of 10. At that improved sensitivity, cascade halos that Fermi could not detect may become visible to CTA. If CTA detects the halos, their angular size and energy spectrum will constrain the field precisely. The halo size depends on field strength. Stronger fields deflect more and produce a wider halo. Measuring both would simultaneously determine field strength and spatial correlation structure. If CTA still finds no halos, even at its improved sensitivity, the lower bound on the field tightens. Both outcomes, detection and non-detection, advance the quantitative understanding of the field. The combination of CTA and SKA measurements, expected through the late 2020s and 2030s, will provide the first constraints precise enough to distinguish between competing origin scenarios. Ultra-high-energy cosmic rays offer a third, completely independent method for probing the field. Cosmic rays are charged particles accelerated to enormous energies by violent astrophysical events. The highest energy cosmic rays carry more than 10 to the 20th electron volts per particle. Such particles travel nearly straight through weak fields, deflected only slightly by stronger ones. But even the extremely weak intergalactic field deflects particles measurably over great distances. A ray traveling 500 megaparsecs accumulates deflection from the pervasive void field. By studying arrival directions of ultra-high-energy cosmic rays with the Pierre Auger Observatory, astronomers can detect the deflection pattern the intergalactic field imprints over large scales. The magnitude of deflection depends on the field strength and the distance traveled through it. The deflection pattern depends on the coherence length, how far the field maintains one direction. A field with long coherence length produces systematic angular offsets between sources and arrivals. A short coherence length produces scatter in arrival directions rather than systematic offsets. The combination of these effects in Auger data can constrain both properties of the void field. This measurement is entirely independent of both Fermi cascade halos and Faraday rotation measures. Three independent methods constrain the same field through completely different physical processes. When all three converge on consistent values, the case for a primordial field becomes definitive. The field's spatial power spectrum is arguably the most diagnostic observable for theoretical tests. Power spectrum describes how field energy is distributed across different spatial length scales. Fields generated during inflation have a characteristic spectrum dictated by inflationary dynamics. Fields generated during electroweak symmetry breaking have a spectrum shaped by that transition. Fields generated during baryogenesis processes have yet another characteristic scale distribution. Each scenario predicts a correlation length, how far the field direction stays coherent in space. Kaniashvili's group has published predicted power spectra for each major theoretical class. Those predictions can be tested once SKA delivers rotation measure data at sufficient density. The comparison requires no subjective interpretation. The spectra are quantitatively distinct. A field with an inflationary origin has a smooth, nearly scale-invariant correlation structure. A field from electroweak turbulence peaks at a scale set by the bubble collision size. A field from QCD processes has a peak at a larger scale corresponding to the QCD horizon size. Measuring which spectrum matches the data will identify the epoch of field creation precisely. The primordial field also left imprints on cosmic structures that formed long after it was created. Magnetic fields influence how gas collapses to form stars and galaxies in subtle, measurable ways. Charged particles in a magnetic field spiral around field lines rather than falling freely inward. This affects the collapse rate, the angular momentum distribution, and the resulting star formation. A strong primordial field could have suppressed the formation of the very smallest early structures. Alternatively, it could have enhanced early galaxy formation by providing extra angular momentum. A primordial field also provides a built-in seed for the galactic dynamo in every forming galaxy. Without a seed, the galactic dynamo must bootstrap from quantum fluctuations, a very slow process. With a primordial seed in place, galaxies can develop strong internal fields far more quickly. The timing of magnetic field growth in early galaxies would be dramatically different in each case. Radio observations of very distant galaxies, seen when the universe was under 1 billion years old, can probe magnetic field strengths during the epoch when the first galaxies assembled from gas. If early galaxies show fields stronger than the local dynamo could produce in their brief lifetimes, that excess points directly to a primordial seed inherited from the intergalactic void field. Webb can identify galaxies at redshift 6 and beyond with remarkable infrared sensitivity. ALMA can detect radio emission from magnetic fields in early galaxies at millimeter wavelengths. When combined, both instruments access the magnetic history of the universe's first 1 billion years. SKA will eventually extend this reach to earlier times and to far larger samples of early galaxies. The intergalactic field also constrains the origin of the highest energy particles in the universe. Ultra-high energy cosmic rays must have been produced nearby, within a few hundred megaparsecs. At those energies, particles interact with microwave background photons and lose energy rapidly. A particle produced more than a few hundred megaparsecs away cannot survive the journey intact. This means sources of ultra-high energy cosmic rays should be identifiable from arrival patterns. But the observed arrival directions do not point cleanly back to obvious source populations. The intergalactic magnetic field provides part of the explanation for this directional confusion. Deflection by the field smears the arrival directions away from the true source positions. The smearing depends on the field strength and coherence length in the intervening volume. By modeling the expected smearing and comparing to observed arrival distributions, theorists can constrain the field properties independently of all other measurement approaches. Auger keeps collecting ultra-high energy cosmic rays and refining its measurement methods each year. The telescope array in Utah provides a complementary sample from the northern hemisphere sky. Together, Auger and the telescope array cover the entire sky for ultra-high energy cosmic ray data. Their growing combined statistics provide an increasingly precise probe of the void field. The investigation of the intergalactic magnetic field connects to the deepest questions in physics. Magnetic fields at cosmological scales probe physics that no accelerator will ever directly achieve. The Large Hadron Collider achieves roughly 14 trillion electron volts in proton collisions. The electroweak transition occurred at approximately 100,000 trillion electron volts. The gap between LHC's reach and the electroweak transition is a factor of roughly 10 million. No accelerator ever built on Earth would close that gap by more than a small fraction. The early universe is the only laboratory where electroweak scale physics was directly realized. The intergalactic field is potentially the only surviving relic of that laboratory we can measure. The large-scale structure, the cosmic microwave background, the light element abundances, all carry information about the universe at different epochs and different energy scales. But the intergalactic field, if primordial, carries specific information about the first second. It carries information encoded differently from any other cosmological observable we possess. When Nerenov and Vogt published a 2010 paper, the community reaction was mixed and cautious. Some physicists were skeptical that absent halos could be uniquely attributed to a magnetic field. Other explanations for missing halos were proposed and investigated over the following years. Perhaps the blazars were not continuous emitters over the timescales needed for cascade formation. Perhaps cascade photons were absorbed by unknown processes along the way to Earth. Perhaps Fermi had systematic effects that suppressed extended emission around point-like sources. Each of these alternatives was examined carefully and tested against all available data. The variability explanation was constrained by observations showing cascade timescales exceeded it. The absorption hypothesis was constrained by the observed spectra of the blazars themselves. The instrumental systematic was tested by injecting simulated halos and recovering them correctly. None of the alternatives could explain the observations consistently with all available constraints. By 2020, consensus had shifted firmly toward accepting the primordial field interpretation. The debate moved from whether the field exists to why it exists, a significant conceptual shift. This shift in how the question is framed reflects a maturation of the field's scientific status. In its early years, the intergalactic field was an anomaly that scientists hoped to explain away. Today, it is an accepted feature of the universe, requiring an explanation within cosmological theory. This transition from anomaly to accepted feature happens repeatedly in the history of cosmology. Dark matter was dismissed as an accounting error before becoming a pillar of the standard model. Dark energy was dismissed before supernova data forced its acceptance into the standard model. The cosmic microwave background was initially called receiver noise before its cosmological origin. Each transition happened when the observational evidence became too strong to explain away. The intergalactic magnetic field has followed the same trajectory over the past 15 years. It is now a feature of the universe that must be incorporated into any complete cosmological model. And like dark matter and dark energy before it, its origin is poorly understood, despite its reality. There is a deeper philosophical dimension to this field that technical papers rarely articulate. Everything we can observe, galaxies, stars, planets, biological life, emerged from the Big Bang. These structures condensed out of the early universe over hundreds of millions to billions of years. Recombination occurred 380,000 years after the Big Bang, when electrons joined protons to form atoms. Before recombination, the universe was opaque. Light could not travel freely through the plasma. The cosmic microwave background is light from recombination, the earliest photons we can observe. The intergalactic field, if born at the electroweak transition 1 second after the Big Bang, predates the cosmic microwave background by nearly 380,000 years of cosmic history. It predates the formation of any atom in the universe, any nucleus, any structure of any kind. It was present in the universe before any of the physical objects we observe today had formed. The void, the region of the universe most devoid of all structure and formation. is the place where the most ancient surviving record of the early universe has been preserved. The absence of structure is exactly what protected this record from being erased by later processes. Dense regions near galaxies have been magnetically stirred and amplified far beyond recognition. The voids, untouched by any significant astrophysical process since the Big Bang, remain pristine. Reading the void field is therefore reading the universe's oldest surviving magnetic archive. The archive is encoded in 4 measurable properties that different instruments probe differently. The field strength, how intense the field is in the deepest voids, is constrained by Fermi halos. The coherence length, over what scale field direction stays correlated, comes from power spectra. The helicity, net-handedness of field line twisting, comes from cascade pattern asymmetries. The spatial variation from voids to filaments is measured through Faraday rotation maps from SKA. Together, these 4 properties define the field completely enough to identify its origin mechanism. No single instrument can measure all 4 properties simultaneously with sufficient precision. The combination of Fermi, CTA, SKA, and cosmic ray arrays collectively covers all 4 measurements. The intellectual project is not a single observation, but a coordinated multi-instrument campaign. It spans radio to gamma-ray wavelengths, from the smallest dipole to the largest mirror array. It involves theorists, simulators, observers, and engineers working across multiple continents. The timeline for resolution is not indefinite. The instruments are real and progress is measurable. SKA Phase 1 first light occurred in 2024, with initial data quality characterization underway. Full science operations with the Rotation Measure Survey will develop through the late 2020s. The CTA Northern Array at La Palma has been commissioning its first telescope units since 2023. Full array completion and deep blazar observation programs are expected through the early 2030s. Each instrument contributes a piece that alone is insufficient, but together is decisive. Within 15 years, the combination should resolve the intergalactic magnetic field's origin. That resolution will have consequences beyond the question of one cosmological magnetic field. If the field formed during electroweak breaking, it directly confirms that transition's dynamics. The electroweak transition is predicted by the standard model, but never probed in any laboratory. The type of transition, first order with bubble nucleation, or second order and smooth, determines whether gravitational waves were also generated that space-based detectors could find. The Laser Interferometer Space Antenna, LISA, is scheduled for launch in the 2030s. LISA is sensitive to gravitational wave backgrounds from first-order cosmological phase transitions. If the electroweak transition was first order, which bubble-based magnetogenesis requires, LISA should detect the gravitational wave background that the same transition produced. A detection of the intergalactic magnetic field with electroweak characteristics, combined with the LISA detection of gravitational waves at the corresponding frequency, would constitute direct confirmation of electroweak physics at the transition energy. That would be the most precise test of particle physics at the electroweak scale ever achieved. It would far exceed the cosmological implications of anything the LHC has measured. If instead the field was generated during inflation, it constrains inflationary models directly. Many models of inflation exist, each with different scalar fields driving the expansion. Inflationary magnetogenesis depends on coupling between the inflaton and the electromagnetic sector. Different couplings produce different field strengths and different correlation structures. A measured field strength and power spectrum would select among the competing inflationary models. In a field where models proliferate and observational constraints are scarce, any discriminating measurement has enormous scientific value beyond the specific question. The link between the intergalactic field and the matter-antimatter asymmetry is equally profound. If the same process created the field and created the matter excess, the two are inseparable. Measuring the field's helicity would directly probe the parity-violating process that generated it. If that process was electroweak baryogenesis that created matter's dominance, helicity is expected. If helicity is detected at the level consistent with electroweak baryogenesis predictions, it would provide indirect confirmation of why the universe is made of matter rather than antimatter. That question, why we exist at all rather than being annihilated at the Big Bang, has checkout. has been one of the deepest unsolved problems in physics for as long as it has been posed. The intergalactic magnetic field, threading the empty voids millions of light years from any galaxy, may carry the answer encoded in the twist of its field lines across cosmological distances. The universe ran an experiment in its first second that no laboratory will ever reproduce. The conditions of that experiment left physical imprints across the universe that persist today. Most of those imprints have been diluted, mixed, processed, and made unreadable by later evolution. The intergalactic magnetic field in the voids is one of the few exceptions that remains readable. The voids preserved it because nothing happened there. No stars, no galaxies, no dynamics at all. The most featureless regions of the observable universe are its most faithful ancient archives. Reading that archive requires instruments of unprecedented sensitivity spread across the planet. It requires theorists who can predict what each possible origin scenario would leave behind. Building instruments over decades and analyzing data for years requires enormous, sustained patience. All of these conditions are now being met simultaneously for the first time in this investigation. The instruments are being built, the theories developed, the collaborations assembled. The timelines are measured in years rather than generations. This question will be answered within the professional lifetimes of the researchers currently working on this specific question. The intergalactic magnetic field's origin should shift from unknown to measured and understood. What will be found is genuinely uncertain. The evidence does not yet favor one scenario strongly. The inflation hypothesis, the electroweak scenario, and the Baryogenesis connection all remain open. Each has theoretical advocates and observational constraints that have not yet been decisive. The uncertainty is part of what makes this one of the most genuinely open questions in cosmology. Not a question where the answer is known, but the measurement is difficult to make in practice. A question where the answer is unknown because the right measurement has simply not yet been made. Understanding why the universe is permeated with a magnetic field will not only answer one question, it will illuminate what the universe was doing in its first second, before any atom or star formed. It will connect cosmological observation to particle physics far beyond any accelerator's reach. It will potentially resolve why matter dominates over antimatter in the same single measurement. And it will confirm that the empty voids, long assumed to be nature's least interesting regions, are in fact the most precious archives of the universe's earliest and most extreme conditions. Thank you for following this journey through the universe's oldest and most invisible structure. If this moved you, subscribe and stay for the next chapter of what the early universe left behind. Your curiosity about the invisible is what drives the instruments that eventually make it visible.